Friends of mathematics, welcome back. This is section 4.6, video B, and the problem is the magic rectangle. A rectangle is changing shape, and by shape, I mean the signs are changing. One side is getting longer at a rate of 3 inches per minute, while another is getting shorter at 1 inch per minute. How fast is the area changing when the rectangle or when the respective side lengths are 13 and 9 inches? And we can see right off the bat that these sides are functions of time. And so we're going to have this related rate and this idea of implicit differentiation going down. So step 1 is to identify what we have. And so I'm going to refer to this as dx dt. And we'll say that that's 3 inches per minute. And I think it's pretty clear that that is a derivative. On the other hand, we have another side getting shorter at 1 inch per minute. And so I can call this one dy dt. But I should take note that because the side is getting shorter, this is going to be a -1 inches per minute. Now, we have our ideas here. We have our rates. What we're looking for is dA dt. How is the area changing? And this is going to go down when it looks like x is equal to 13 and y is equal to 9. So that's step 1. Step 2 is for us to make a picture. And my picture is not going to involve dx dt, even though I can say that the side is getting bigger here and that this one is getting smaller, but this total length is x and that total length is y. Once we have this, it's up to us to now make our relationship. And the relationship that we're going to be looking at is this geometric relationship that a is equal to x times y. When we're done with that, now it's time to take the derivative. We should keep in mind that the derivative of every single one of these quantities is a function of time. So on this side, the derivative is going to be dA dt. On this side, I'm going to have to use the product rule to get down. So the derivative of x is going to be dx dt times y, which we get for free, plus x times the derivative of y, which is dy dt, and we're done taking our derivative. Our next step is to maybe solve for our unknown derivative, and our unknown is dA dt, and so this part's already done for us. And we're finally going to plug in. And what can I plug in here? dA dt we don't know. We certainly know dx dt, and that was 3. When did we want to know how the area was changing? Oh, when x was 13 and y was 9. And so I'm going to plug that value in. I can plug in our x value, which is 13. And dy dt, because the height was getting smaller, -1. This gives us a glorious 27 minus 13, so 14. Now, the one thing that I do like to check is what are the units of this? And the 3 was in inches per minute. The 9 was in inches. And so isn't that wonderful? Square inches per minute, which is exactly how the area would be changing. So our final idea here is to make a self-check. And sure, this rectangle is getting, the shapes are changing, the height is getting smaller, and the width is getting bigger. Now, the width is getting bigger faster than the height is getting smaller, and we did this when the width is indeed larger than the height, so it makes sense to me that the area was getting bigger. And how was it getting bigger? Well, at this moment of time, it was getting bigger by 14 square inches per minute. All right, friends, that's our magic rectangle. Next, we're going to look at a Pythagorean theorem related rate problem.